Previously on Physicsball Z, our heroes journeyed to the shocking analogy between gravitational potential energy and electrical potential energy, and just when they armed themselves with the powerful equations to overcome electrical resistance, they were attacked by this past paper question. But with the help of some ancient highlights, they were able to answer the question and collect all of the marks. And now, the series has moved into a parallel universe with interesting consequences and ideas. Will our heroes be able to describe the differences between series and parallel circuits, or will they find the whole situation too shocking to handle? Find out in today's episode of Physicsball Z. Here are the retrieval questions for this lesson. You know what to do. The potential difference moves the current in a circuit. Resistance is measured in ohms. Fermentation is anaerobic respiration in plants and yeast. Xylem tissues carry water and minerals around the plant. Sublimation is a solid turning into a gas. Condensation is a gas turning into a liquid. Before we look in depth at series and parallel circuits, we'll do two activities just to warm ourselves up. I've got these two circuits and a graph below. Complete these challenge questions. In circuit 1, the current is 0.3 amps, and in circuit 2, the current is minus 0.3 amps. If you look closely, you see that the battery is reversed, which means that the current is flowing in the opposite direction. From the last video, we looked at three graphs, and the one that is directly proportional, meaning that it's a straight line going through the origin, is a resistor. Check out the previous video if you need to see the other two graphs. In this activity, I have these four circuits. Now try and answer these challenge questions. We should connect voltmeters the way you see it in circuit 1. And we should connect ammeters the way you see it in circuit 4. This next one's a bit trickier. Ammeters are connected in series. That means within the same loop of wire. But voltmeters are connected in parallel, so they're branched off in a separate wire. Here we have a series and a parallel circuit. The spark represents the current flowing from the battery. If we follow the spark in the series circuit, the same spark goes into light bulb 1 and then into light bulb 2. But for the parallel circuit, we notice that the spark splits where the wire branches off. Also, we notice that if there's a circuit break, something interesting will happen in both series and parallel circuits. This diagram shows how ammeters and voltmeters read in series and parallel circuits. Pay close attention to the cell and the potential differences. Now have a go at these challenge questions. We saw that the same spark moved out of the battery and through the whole loop in a series circuit, so that means that the current must be the same everywhere. Parallel circuits have their potential differences identical around the circuit. And for the final question, we see that the current can still flow down the other complete path. This is why some decorative lights use parallel circuits so that not all the lights turn off if one of the light bulbs break. We can summarize this information as this. Series circuits, the current is the same everywhere but the potential difference varies. And for parallel circuits, the current varies but the potential difference is the same. This next part concerns how you calculate resistance in a series and parallel circuit. This is what that would look like. The total resistance in a series circuit is the sum of all the resistors in the circuit. That seems pretty straightforward, we just add up all the resistors. But in a parallel circuit, it's not that straightforward. The total resistance is less than the resistor with the least resistance.
Oh my god.
I know, it's a bit mad, but let me get Jaden for this. Jaden.
What one?
Using this sentence, what must be the total resistance in this circuit?
Do we need an equation for this?
No, just this sentence.
This is long.
Okay, which resistor has the lowest resistance?
The first one in it.
Good work. What's the resistance?
1.
It's best to use the unit, so yeah, 1 ohm. Now, use this sentence to tell me what the total resistance is here.
What, it's less than 1, yeah?
The total resistance in this circuit will be less than 1. An analogy that we sometimes use is a motorway. The resistors represent the toll booth and the moving cars represent the current. The current is slowed by the resistors, just how a toll booth slows down the speed of the traffic. And if you add toll booths on the same road, you would decrease the traffic even further, which is the same as increasing the resistance in the circuit. You're adding it all in one loop of wire. However, if the toll booths are on different lanes, the speed is not going to be slowed down as much as if there was just one lane. You do not need to know the actual calculations for this. Just repeat whenever they ask you what the total resistance is. Just be aware that the total resistance will be less than the resistor with the least resistance. That's literally all you have to be aware of. With that all said now, see if you can answer this question. The resistance of the lamp is 10 ohms, and each resistor itself is also 10 ohms. The resistors are in parallel, which means that the total resistance of both is less than 10. Therefore, 10 ohms from the lamp plus less than 10 ohms from the resistor means that the only option that we have here must be less than 20 ohms. Since we're here, I might as well just go ham with the past paper questions. And so this is how we're going to write it for the next question when we're explaining our reasons. The first reason is that the resistance of the bulb is 10 ohms, and in series the resistors add up. But the resistance in parallel have a total resistance of less than 10, so 10 plus less than 10 must mean that we have less than 20. This question is going to link the episode I did on current and potential difference. A student built a circuit using a filament lamp. Now sketch a current potential difference graph for a filament lamp. See if you can collect the 2 marks here. What should we draw? This is how you should have drawn that. There is 1 mark for having a curve in these 2 sections here, and that curve must go through the origin. And the second mark, you have to show the curve having a decrease in gradient, so they're curving away from your y-axis. The next question shows a circuit with 2 identical filament lamps. Compare the current for 1, 2 and 3. Do your thing. This is a parallel circuit, so we need this summary. Current 1 splits into current 2 and current 3. This means that current 1 is equal to the sum of current 2 and current 3. This also means that current 2 is equal to current 3, because the lamps are identical, so they both have the same resistance. This next question is a bit mad. It's asking you to calculate the charge that flows through the cell in 1 minute. Each filament lamp has a power of 3 watts and a resistance of 12 ohms. Write any equations that you use. Give the units. You're gonna need 2 equations here from some of my previous episodes. See if you can answer this. We have power and resistance, which means one of the equations that we need here is power equals current squared times resistance. And to then get the charge flow, we need this equation here. Current equals charge flow over time. This means that current squared is equal to 3 watts over 12 ohms. Current is therefore the square root of 3 over 12, which is the square root of 0.25. This gives us 0.5 amps. That's our current. Now we rearrange the charge flow equation. Before we calculate, we need to convert 1 minute into 60 seconds. And 0.5 times 60 will give us 30 coulombs. Okay? Don't forget that the unit for charge flow is coulombs. And there we go. Mission complete.
Fatality.
Check the descriptions, use the timestamps, go where you need to go, and I'll catch you guys in a bit.